Hello. Thanks for coming in today. We are looking for a senior professional to join our VFX team, and looking at your portfolio, you have a really impressive track record over the last 5 years. To start things off, let's just keep it casual. Can you tell me a bit about how you generally approach a new project when you are leading a module?
Thanks for having me. When I step into a lead role for a module, my first priority is always to bridge the gap between the creative vision and the technical constraints. I usually start by conducting a deep dive into the artistic goals. What is the director actually trying to evoke? Once I have a handle on that, I look at the pipeline. I want to know where the bottlenecks are and how we can build a scalable solution. I try not to just solve the immediate problem for one shot, but to design a workflow that the entire team can use across the whole sequence. It is all about creating a predictable, repeatable process so that the artists can focus on the art rather than fighting the software.
That makes sense. Speaking of fighting the software, let's dive into some of the fundamentals to get a feel for your technical grounding. It sounds simple, but in a high-pressure pipeline, we rely heavily on the basic tools. For instance, from a pipeline perspective, what would you say is the primary purpose of the undo function?
It sounds basic, but the undo function is really the backbone of artistic experimentation. Its primary purpose is to allow artists to reverse their last action or a series of actions, which lets them correct mistakes or experiment with a look without the fear of permanently altering their work. In a professional VFX pipeline, where we are often iterating on high-poly models or complex composites, having a reliable way to backtrack saves an enormous amount of time. It reduces frustration and allows for a more fluid creative process because an artist can try a bold approach, and if it doesn't work, they can revert in a second and try something else.
Right, it's about the freedom to fail quickly. Now, moving into compositing, let's talk about layers. Can you explain what the alpha channel represents, and why it is so critical when we are blending elements?
The alpha channel is essentially the transparency map of an image. While the RGB channels handle the color, the alpha channel determines how opaque or see-through each pixel is. In technical terms, a value of 1 or 100% means the pixel is fully opaque, and a value of 0 or 0% means it is completely transparent. This is absolutely essential for combining multiple elements realistically. For example, if we are adding a CG character into a live-action background, the alpha channel ensures the character is cut out perfectly from its original render plane, allowing the background to show through the transparent areas. Without a clean alpha, you end up with visible edges or halos around your objects, which immediately breaks the illusion.
Definitely. And speaking of illusions, let's talk about organic materials. When you're overseeing the look dev of a character, you'll often hear the team talking about subsurface scattering. Can you explain what SSS is, and why we can't just use a standard diffuse map for something like human skin?
Subsurface scattering, or SSS, is a lighting effect where light doesn't just bounce off the surface of an object, but actually penetrates the material, bounces around inside the volume, and then exits at a different point. This creates that soft, diffused glow we see in translucent materials. For organic materials like skin, it is non-negotiable. Real skin isn't a solid, opaque shell, it has depth. Light enters the epidermis, scatters through the dermis, and reflects back. If we don't use SSS, skin looks flat, waxy, or like plastic. It lacks the warmth and the internal depth that makes a human look alive. When I'm reviewing renders, if a character looks uncanny or too hard, SSS is usually the first thing I check to ensure the light is bleeding through the ears or nostrils correctly.
Let's shift gears into the more technical side of things, specifically simulations. You've led several complex shots. Let's say you're reviewing a simulation, and you notice jiggle or some general numerical instability. What are the 3 most common root causes you look for, and how do you fix them?
Jiggle and instability are usually a sign that the solver is struggling to find an equilibrium. The first thing I look at is the time step. If the time step is too large, the solver essentially skips over the subtle changes in motion and overshoots the target, which creates those unnatural vibrations. The solution there is to reduce the time step size, which allows the simulation to capture finer details and stabilize. Second, I look for stiff forces or constraints. When you have extreme values, like a very rigid spring or a hard constraint, it can introduce high-frequency noise because the solver is fighting to balance those extreme forces. To fix this, I'll either add damping to soak up that energy or suggest moving to an implicit integration method, which is generally more stable for stiff systems. Third, I check the geometry and collisions. Poorly conditioned geometry, like overlapping faces or extremely thin slivers, can cause erratic movements when objects intersect. In those cases, I'll focus on smoothing the collision meshes, increasing the collision margins to create a small buffer, or using softer constraints to prevent the physics engine from exploding on impact.
That's a very systematic approach. Now, thinking about the movement itself, we often mix different techniques. From your perspective, what is the fundamental difference between keyframe animation and procedural animation, and how do you decide which one to use for a specific shot?
The difference really comes down to the source of the motion. Keyframe animation is a manual process. An animator sets specific poses at different points in time, and the software interpolates the movement between those keys. This gives the artist absolute frame-by-frame control over the timing, the arc, and the emotional nuance of the performance. It is a very hands-on, artistic approach. Procedural animation, however, is rule-based. Instead of posing the character, we define a set of algorithms or parameters, like move toward this target but avoid this obstacle, and the system calculates the motion dynamically. In terms of decision-making, I use keyframes for hero performances where the emotion and specific timing are critical. But for secondary motion, like a crowd of people walking or the way a cape flutters in the wind, I'll push for a procedural approach. It is much more scalable. You can't manually keyframe 1,000 soldiers in a battle, but you can build a procedural system that governs their behavior, and then layer a few keyframed hero animations on top for the focal points.
Speaking of the creative process, you'll often deal with clients who have a vision that defies physics. Imagine a client insists on a highly stylized look for the CG elements, something that deviates significantly from reality. As a technical lead, how do you guide the implementation while still respecting that artistic vision?
That is always a delicate balance. My first step is to strip away the technical jargon and break the stylized look down into its core visual components. Is it exaggerated proportions? Non-realistic lighting? Unique painterly textures? I'll sit down with the client and identify what is a must-have and where we have some wiggle room for efficiency. I find that using references from other films or games is the best way to align expectations, so we are all speaking the same visual language. Technically, the key is flexibility. I avoid baking in too many decisions early on. I'll prioritize procedural shading or customizable rigs that allow us to tweak the look without having to rebuild the entire asset. I also implement a tight feedback loop. I'll share work-in-progress renders frequently. By showing the client the progression, I can steer the technical implementation in a way that satisfies the vision while keeping the pipeline manageable. It's about saying, yes, we can do that, but then figuring out the most sustainable way to execute it.
Let's jump back to some core pipeline concepts. For the sake of the junior artists on the team, how would you explain the basic function of a depth map?
I usually explain a depth map as a grayscale representation of distance. In a depth map, the brightness of a pixel corresponds to how far that object is from the camera. Typically, lighter areas are closer to the lens, and darker areas are farther away. It's an incredibly powerful tool for post-production. We use it to generate realistic depth of field effects, adding atmospheric fog that thickens as things get farther away, or integrating 2D elements into a 3D space. It basically gives the compositing team a map of the 3D scene's volume without needing the full 3D geometry.
Now, render engines. You've likely worked with Arnold, V-Ray, and maybe others. How does the choice of a render engine typically affect the final look and the overall workflow of a project?
The choice of engine impacts both the aesthetic and the logistics. Different engines use different algorithms for global illumination and lighting. Arnold, for example, is renowned for its physical accuracy and out-of-the-box realism, which makes it a go-to for high-end photorealism. V-Ray, on the other hand, often provides more flexibility with its settings, which can be a huge advantage for architectural visualization or when you need a more stylized, controlled look. From a workflow perspective, integration is key. If the team is heavily using Maya, Arnold's integration is seamless. If they are in 3ds Max, V-Ray might be the more natural fit. Render speed and resource usage also vary wildly. Some engines handle massive amounts of geometry better, while others are more efficient with complex lighting. As a lead, I consider the hardware we have available and the specific look of the film before picking the engine. I also look at the ecosystem. The available plugins and presets can significantly speed up the production timeline.
When we're moving assets around, specifically rigged characters, what file format are you using to ensure everything transfers correctly between different software packages?
In almost every professional pipeline, FBX is the standard. It's widely supported across Maya, Blender, and Unreal Engine. The reason we use FBX is that it doesn't just carry the geometry. It preserves the skeleton, the animation data, and even basic material assignments. When you are transferring a rigged character, you can't afford to lose the joint hierarchy or the animation keys. FBX provides a reliable way to package that data so it remains consistent as it moves from the rigging department to the animation department, and finally into the render engine.
Let's talk more about that rigging process. What is the primary purpose of an armature, and why is it the foundation of character movement?
The armature is essentially the digital skeleton of the character. Its primary purpose is to provide a control structure that allows animators to deform the 3D mesh in a realistic and flexible way. Without an armature, a character is just a static skin, a mesh. The armature consists of a hierarchy of joints and bones that define how the limbs bend, how the spine twists, and how the character rotates. By manipulating the armature, we can create complex poses and animations while the software handles the deformation of the skin around those bones. It transforms a piece of digital sculpture into a performative actor.
Now let's talk about scale. Imagine a shot where you need to simulate hundreds of interactions, like a glass window shattering on impact into 1,000 pieces. What procedural tools or solvers would you employ to handle that, and why?
For a shot like that, I would rely on a combination of rigid body dynamics and fracture solvers. I wouldn't even dream of animating that by hand. I'd likely use Houdini, specifically using a Voronoi fracture node to generate the actual shards. Voronoi is great because it breaks the geometry into natural-looking fragments based on a set of seed points. Once the geometry is fractured, I would feed it into a rigid body solver like the bullet solver. This allows the physics engine to calculate the collisions and the way the glass pieces bounce and slide based on the impact force. To make it feel truly cinematic, I'd add secondary effects. I'd use particle systems to create a cloud of fine glass dust and small debris that lingers in the air. By combining the heavy lifting of the rigid body solver with a lighter particle simulation, you get a result that is both physically believable and visually rich, all while remaining scalable.
Let's move into post-production for a moment. Scenario: the camera is moving very quickly past an object. The render looks a bit too clean and sterile. What visual technique can you use in post to enhance that sense of motion blur?
If the render feels too sharp, I would apply a directional motion blur effect in the compositing stage. This simulates the natural streak that occurs when an object moves across the frame faster than the shutter speed can capture. I would apply the blur in the exact direction of the camera's movement, and then tune the intensity to match the perceived speed. This is a huge time saver because it allows us to achieve a high-speed feel without having to re-render the shot with higher motion blur samples, which can be incredibly expensive in terms of render time.
Let's touch on a basic but vital concept: frame rate. How do you explain frame rate to a client, and why does it matter for the feel of the animation?
I describe frame rate as the number of individual images, or frames that are displayed every second, which we call FPS. It is essentially the resolution of time. A higher frame rate like 60 FPS results in motion that is incredibly smooth and fluid, which is often used in gaming or high-action sports. A lower frame rate like 24 FPS is the cinematic standard. It has a slight choppiness that we have been conditioned to associate with movies. If you change the frame rate, you change the entire psychological feel of the piece. If a shot is intended to be a dreamy, cinematic moment but is rendered at 60 FPS, it can feel like a soap opera or a home video.
I want to go back to the characters. Let's say we have a shot, and the feedback is that the character's face looks stiff and robotic. As a lead, what 3 technical or artistic adjustments do you suggest to the team to improve the emotional range?
First, I would tell them to look at the timing and spacing. Robotic movement usually happens when transitions between expressions are too linear. I'd have them refine the animation curves to create more organic, ease-in and ease-out transitions, making the movement feel like it's driven by muscle and bone rather than a computer. Second, I would push for the addition of secondary motions. In real life, faces are never perfectly still. I'd suggest adding micro-expressions, slight eyebrow twitches, small tremors in the cheek, or a slight quiver of the lip. These tiny, almost subconscious movements break the stiffness and signal to the audience that the character is thinking and feeling. Third, I'd encourage them to slightly exaggerate the key poses. In animation, if you do exactly what a human does, it often looks muted or dead on screen. By pushing the emotional peaks of the expression just a bit further, you ensure that the emotion reads clearly to the viewer, even in a fast-paced scene.
That's a great breakdown. Now, I want to push you on a high-level conceptual question. How would you go about building a nonlinear character interaction system that adapts organically to unpredictable environmental changes? I'm talking about something that doesn't rely on fixed scripts.
That's a fascinating challenge. To build something like that, I would move away from linear timelines and instead design a modular behavior framework. Instead of a script that says, at frame 100 the character reacts to the explosion, I would give the character a set of core traits, goals, and emotional states. The system would rely on real-time sensory input. I'd implement a layer that monitors the environment for physics events, object states, or the actions of other characters. This input would then feed into a decision-making layer, something like a behavior tree or a utility-based AI. The AI would evaluate the environment against the character's current state. For example, if the character is brave and sees a fire, they might move toward it. If they are cowardly, they'd trigger a retreat behavior. Then, to make the execution feel natural, I would blend procedural animation with a library of pre-authored movements. This way, the transition from a walk to a flinch or a jump is handled dynamically based on the environment. The goal is to create a system where the character is reacting to the world in real time, creating an interaction that feels unscripted and organic, but still remains consistent with the characters. Established personality.
That sounds like a very robust architecture. Let's move back to the production side. Can you explain the baking process in animation? Why do we do it, and what is the trade-off?
Baking is the process of taking complex simulations, procedural calculations, or constraints, and permanently applying them to the actual keyframes or geometry of an object. Think of it like this. Instead of the computer calculating the physics of a waving flag every single time you hit play, baking stores the final position of every vertex for every frame directly into the data. The primary advantage is performance. Once a simulation is baked, the scene runs much faster and more efficiently because the CPU no longer has to solve complex math in real time. It also ensures that the animation is consistent across different machines. The trade-off, of course, is flexibility. Once you bake something, you can't easily change a parameter, like the wind speed of that flag, without rebaking the whole thing. It's essentially pre-cooking the meal so it's ready to serve, but you can't change the ingredients once it's in the oven.
Interesting. Now let's discuss null space. This is a term that comes up in 2 different contexts. First, in the context of movement and performance, how does controlling null space add life or imperfection to a character?
In terms of performance, null space refers to those subtle, seemingly random movements that happen between the main poses. It's the noise of human existence. In the real world, we don't move with mathematical precision. We sway, we hesitate, we slightly overshoot our target. By intentionally adding null space into an animation, we break up that mechanical, computer-generated perfection. For example, if a character is reaching for a coffee cup, a robotic animation goes in a straight line and stops exactly at the handle. A human-like animation will have a bit of null space. The hand might slightly overshoot, the shoulder might shift a bit as they lean in, and there might be a tiny correction right before the grasp. Those imperfections are what actually make a character feel alive and believable to an audience.
Now, contrast that with the rigging side. What is null space in the context of a rigging setup, and why is it something we have to avoid?
It is a bit confusing because the term is used differently, but in rigging, null space is a technical failure. It refers to a situation where a joint or a control has absolutely no influence over the deformation of the mesh. This happens when the joint's transformations aren't properly connected to the skin weights, or if its influence is completely overridden by other joints. This must be avoided because it creates dead weight in the rig. It adds unnecessary complexity to the scene and can lead to confusing results for the animator. Imagine an animator selecting a control, moving it, and seeing absolutely nothing happen on the mesh. That is incredibly frustrating and slows down production. A clean, professional rig should have a one-to-one relationship between a control's purpose and the resulting deformation. Every joint should serve a clear, functional purpose.
Fair enough. Let's talk principles. If you were mentoring a junior animator, what are 3 essential animation principles you would tell them govern believable movement?
I'd start with squash and stretch. This is all about giving objects a sense of weight and flexibility. If a ball hits the ground, it shouldn't just stop. It should flatten slightly on impact and stretch as it bounces back up. It prevents the animation from looking rigid. Next is anticipation. This is the wind-up before the action. If a character is about to sprint, they don't just move forward, they lean back and coil their muscles first. Anticipation tells the audience what is about to happen and makes the subsequent action feel powerful and earned. Finally, follow-through and overlapping action. This is the idea that different parts of a body move at different speeds and stop at different times. If a character stops running abruptly, their hair, their clothes, and their arms will continue to move forward for a few frames before settling. Without follow-through, movements feel abrupt and mechanical, like a machine switching off.
That's a great summary. Let's talk about the technical side of the animation curves. What do you mean when you talk about readability in the context of animation curves?
Readability is all about how intuitive the motion is when you look at it in the graph editor. A readable curve has a clear, well-defined shape that immediately tells you the acceleration, deceleration, and timing of the movement. You can glance at the curve and see exactly where the peak of the action is. When curves lose readability, it's usually because they've become too dense or erratic, too many unnecessary control points or jitter in the handles. This makes the motion hard to interpret and, more importantly, incredibly difficult to edit. If another animator has to jump into a shot to make a tweak, they need to be able to read those curves quickly. Good readability ensures the flow of the animation is transparent, making the refinement process much faster.
This has been a very thorough deep dive. You've covered everything from the high-level architectural decisions down to the fine details of animation curves. To wrap things up, do you have any final thoughts on how you see the role of a senior professional evolving in the current VFX landscape?
I think the role is shifting from being just a technical expert to being a bridge. With the rise of real-time engines and AI-assisted tools, the technical barrier to entry is lowering, but the need for strategic thinking is increasing. As a senior, my job isn't just to know how to use the tools, but to know which tools to use and how to structure the pipeline so that the artists can be as creative as possible without being hindered by the tech. I see myself as someone who manages the complexity so that the art can shine.
I really appreciate that perspective. Thank you for your time and for sharing your expertise with us today. We will be in touch very soon regarding the next steps.
Thank you. It was a pleasure. I look forward to hearing from you.